Testing, testing, 1, 2, 3.
Okay, everyone. So let's get started. I'm very happy to have Ilya Mandel here. He's been here, well, since a couple of days. And just a brief introduction to him. He did his PhD, I think he finished around 2009, was it? 7, yeah, 2 years earlier. With a guy named Kip Thorne, you might know him. And I just learned yesterday he played a fundamental role in the production of Interstellar as well, which was mostly dealing with the stuff Kip didn't want to deal with. So yeah, after that, he did a couple of postdoc positions in Northwestern University, more or less in the area of Illinois. And then he went on to become a professor at Birmingham University, where he also, I mean, he became permanent over there, but some people can choose to be picky, and then he decided to move to another position at Monash University. So what things does Ilya like to do? Pretty much everything. So if you chat with him about anything, he will chat back to you and have an opinion on it. But I guess something he's like investing a lot of work right now is population synthesis, the study of gravitational wave sources. And I guess he also leads the development of COMPASS, which is one highly used population synthesis tool. And just a warning, I half jokingly told him, like, you have a Blackboard, you can fill an hour. So he has decided to use a lot of the Blackboard, so you can either thank me or blame me for mentioning it afterwards. So take it away.
Thank you very much, Pablo. Oh, sorry, I forgot to turn this on. Okay, now it should be on. So thanks very much, Pablo, for the very nice introduction. Indeed, I 5 minutes ago was told that I'm actually using the Blackboard, which I'm very excited about. I haven't yet quite decided on the topic, so we'll figure out the topic as we go along. For the Blackboard part. I was told to show one pretty picture, so you can thank one of your colleagues who said that at least one picture is mandatory. So here's the pretty picture, and I will spend 2 minutes telling you about this pretty picture, and then I'll switch to Blackboard stuff, because the pretty picture isn't amenable to back-of-an-envelope calculations, which is really all I know how to do. The pretty picture was made by an artist from Nature at some point to accompany an article that Alison Farmer and I wrote a few years ago, and the pretty picture shows some of the possible channels by which you might make merging binary black holes the sources that gravitational wave observatories like LIGO and Virgo have been detecting in increasing numbers since late 2015. So just to briefly mention some of the channels. So on the left, you have perhaps the classical channel, although I'm not entirely sure anymore that it works in the way that it's drawn here, at least not for binary black hole mergers. So the idea is you start with a pair of two stars. And by the way, let me just say up front that one of the big challenges in gravitational wave astronomy is that at first you say to yourself, well, gravitational waves should be a dime a dozen, right? How many stars are formed? Well, star formation rate is, let's say, something like 1 per 100 cubic megaparsecs in the local universe, 1.5 per 100 cubic megaparsecs. Okay. Then you say to yourself, okay, how many of those stars make neutron stars or black holes? Well, you have about 1 per every 1,000 solar masses of star formation. So if we'll start already with the back-of-the-envelope calculation, because this is the fun part. All right, let me write over here for now. So, okay, so you have something like 1 or 10 to the minus 2 solar masses per megaparsec cubed per year. That's your star formation rate. You have something like 10 to the minus 3 compact objects per solar mass of star formation. Most stars are formed in binaries, so there's some binary fraction, but I'm going to ignore throughout today terms of order unity. Pi equals 2 equals 1 is okay for my purposes. So we'll just ignore that 70% of whatever that comes from binary fraction. Then you say, okay, well, so how many binaries does it mean we're forming? Well, okay, if I multiply these two things together, I get 10 to the minus 5, roughly compact object binaries per cubic megaparsec per year. So another way of writing this is 10 to the 4 mergers of compact objects. So compact object mergers, 10 to the 4 compact object mergers per gigaparsec cubed per year. Now that's actually quite a large number. It's probably about 100 or a few hundred times larger than what LIGO is actually observing in terms of the rates, 100 to 1,000 times larger in terms of the rates of binary black hole mergers. So at first you say, dime a dozen, binary black hole mergers should be super common. In fact, surprised that LIGO isn't seeing more of them. Then you think for a moment and you say, no, it's exactly the opposite. LIGO should never see a binary black hole merger at all. Very simple. If gravitational waves are only efficient when the binary is relatively compact, when the two compact objects are already close together. Even 30 solar mass black holes have to be about 50 solar radii apart in order for that binary to merge within the age of the universe through the emission of gravitational waves. For binary neutron stars, the separation is even smaller. It's only a few solar radii. Meanwhile, very massive stars that give rise to neutron stars and black holes, in general, expand to hundreds, maybe thousands of solar radii during their evolution. So, okay, if I start these two massive stars far enough apart, let's say a few thousand solar radii apart, great. They will form black holes, and then they will just sit there forever. Billions and billions of years, much longer than the lifetime of the universe, we'll never see them merge. If I start them close enough, let's say 50 solar radii apart, well, they will merge long before they make black holes. That might be interesting. You might get some kind of a transient, maybe a luminous red nova or something like that out of it. Lovely, but it's not a gravitational wave source. At least certainly not in the band of gravitational wave detectors on Earth, which are sensitive to gravitational waves at about 100 hertz, actually in the audible band. The thing that LIGO is listening to sounds like this. So it's a chirp because the amplitude goes up and the frequency goes up as the binary gets closer and closer together. But is a lovely signal, but you don't get that at those frequencies if you have two stars that are tens of solar radii apart. So we should never see a gravitational wave source. It was a waste of time to build LIGO. Well, except it wasn't because it saw something, so something is wrong here. So now I'm going to try to tell you a little bit about magic. How do you get around this fundamental problem in gravitational wave astronomy? So magic option number one. You actually start stars far enough apart in a binary, and then you wave a magic wand and you bring them closer together right when they're already small enough, again, to fit into a tight binary. So this is the classical story of isolated binary evolution. Two stars start far apart. One of them expands at some point, initiates mass transfer into the companion after it reaches the end of its main sequence and expands after beyond the main sequence as a giant. That first episode of mass transfer probably doesn't do too much to the binary separation in the grand scheme of things. Then there may be a reverse episode of mass transfer from the companion back onto the primary, which by this point has maybe exploded in a supernova and made a neutron star. That reverse mass transfer, at least in the case of binary neutron stars, as I said, I don't quite believe this anymore, that this works in quite this way for binary black holes, but for binary neutron stars, the reverse mass transfer has a pretty extreme mass ratio because now your neutron star is, let's say, 1.4 solar masses, and your companion might be a 10 or 12 or 15 solar mass star. So at that very extreme mass ratio, mass transfer is dynamically unstable. It goes through a common envelope phase. We might actually talk a little bit about common envelopes later. But this dynamically unstable mass transfer means that as you have a companion, a compact object, neutron star, spiraling through the envelope of a red supergiant, it's experiencing Bondi-Hoyle drag, so there's a lot of energy dissipation. you're converting that orbital energy into heating up the envelope and expanding the envelope. Eventually, you might succeed in expelling the envelope altogether. In the process, of course, you've put in energy from the orbit into unbinding the envelope, and that means that your orbit has lost a lot of energy, so it has shrunk a lot. In fact, it shrinks perhaps by 2 to 3 orders of magnitude. So you might start out at 1,000 solar radii separation and end up at a few solar radii separation, where you now have a neutron star and a naked helium core of the donor, the initial secondary, but the donor during this common envelope phase. And of course, the naked helium core is only about a solar radius in size, so it fits just fine into this very tight binary. And once it collapses into a neutron star, you end up with a neutron star binary, a double pulsar, well, or at least one of them is a double neutron star. One of them may be a pulsar, the other one might not be, depending on how lucky you are. But think of the Hulse-Taylor binary or J0737 or about another 20 such systems known in our own Milky Way. And of course, think of GW170817, which was, many of you may have heard of it. It was a double neutron star merger observed by LIGO, but also detected as a gamma ray burst by Fermi, and then observed as a kilonova and as an X-ray optical and radio afterglow. So we know it's a double neutron star merger. We know the masses. We know that that short gamma ray bursts really do seem to come from double neutron star mergers. Long gamma ray bursts, at least some of them might as well, as we recently found out, but that's a separate story. Great, you've got your compact binary merger. Okay, problem solved by virtue of this magic thing called common envelope, which we will get to a little bit later. Option 2, this is one of Pablo's favorite options. Pablo, in fact, was one of the first people to propose this possibility. He did a very nice job of proposing it. Selma Demink and I did a very quick and dirty job of proposing it almost at the same time. Pablo is much more careful. But the story here is something like the following, and I'll tell the story in an even less careful way. The story is, where's my magic wand? I have a magic wand. Abracadabra, stars, thou shalt not expand. I'm a magician, stars don't expand. Then life is simple. If stars don't expand, right, imagine somehow stars just evolve in the main sequence, and then instead of becoming red supergiants, they become very bright and very blue. They go, instead of going on the Hertzsprung-Russell diagram, instead of going up and to the right, they go up and to the left. Okay, wonderful. Then I can put my two massive stars in a tight binary, 30 solar radii apart, for example, or somewhere in that ballpark. They evolve and make in situ massive black holes, and then those massive black holes are already close enough together to merge with the age of the universe. Done. Okay, how do I make this magic happen? Well, actually, it's the act of putting them in a tight binary that does it for me. Because if I have them in a very tight binary, they end up being tidally locked, and in a tight binary, the orbital period of the binary is short enough, has to be probably order of magnitude a day or less, that, of course, if the stars are also rotating with the same rotational period of a day or less, they end up having meridional circulation. Basically, their poles and their equators are at a very different temperature because they're rapidly rotating, and that means that gas is going to, in the star, is going to circulate. So gas from the outside of the simple picture is gas from the outside of the star, helium, hydrogen-rich gas, comes into the core, and helium fusion products are taken out of the core, back out into the envelope. So instead of having the standard picture at the end of the main sequence where I have a helium-rich core and a hydrogen-rich envelope, and the helium-rich core contracts, and the hydrogen-rich envelope expands by the mirror principle, I don't have an envelope. I've basically fused almost all of the hydrogen in the star into helium. It's a star that just has a core. So the core contracts, it just makes a massive helium star, and that's it. I'm done. That's called chemically homogeneous evolution. So that's the middle picture. The picture on the right it's a slightly different picture because we say, well, sometimes stars don't couple up from zero-age main sequence. They aren't born in a couple. Instead, they might be born single, or they might be born with the wrong companion, maybe not a star massive enough to make a neutron star or a black hole, but they join Tinder. They end up being in some sort of a meet and greet club. Now, meeting and greeting means you have to have other stars around, so it happens in dense stellar environments like nuclear clusters or globular clusters. And in those environments, let's say you have a binary. As I said, let's say that one companion is going to make a black hole, the other one wouldn't even make a black hole, it will make a white dwarf or whatever, and maybe the binary is too wide to ever merge anyway. But at some point, because one of the stars is a black hole, it's heavy, mass segregation works in it, it sinks towards the center of the globular cluster, there it meets another black hole. Another black hole comes by, and the other black hole, the interloper, says, well, I'm heavier than the white dwarf, I'm going to muscle the white dwarf out. That's usually what happens, so the white dwarf just gets kicked out. The black hole comes in, and because it kicked out the white dwarf with a pretty high velocity, conservation of energy tells you that actually the binary now has to shrink. So on average, it's a kind of equipartition where you keep on kicking out stars at high velocities, and that means that you're sharing some of the orbital energy binary with the ejected stars, or ejected black holes, and so your binary is shrinking, and it shrinks and shrinks and shrinks over many interactions until it's tight enough to actually merge within the age of the universe. And that's the dynamical formation scenario. Now, there are other options on all of these things. You can talk about hierarchical triples that are merging through or assisted by Lidov-Kozai resonances. You can talk about mergers in AGN disks where there are both compact objects and gas, and accretion can both help you grow the compact objects and actually can help you bring them together. So lots more variants than are shown here. I'm not going to bore you with going through all of them. I'll instead actually figure out how I can turn off the projector. Give me 1 second. Oh, no, I didn't hold it for long enough. Give me 1 more second. Okay, good. Okay, and now let's go for something completely different. So let's try some fun back-of-the-envelope calculations. And I apologize in advance to people who remember their first-year mechanics well enough that this is all going to be boring. That's fine. I just find it fun to do simple calculations, and also they're the only kind I can manage to do, so bear with me. And I'll talk a little bit about black holes and accretion and maybe common envelopes, and we'll see where we get with this. Now, to begin with, when we talk about black holes swallowing mass, for example, through an accretion disk, one of the really exciting bits about this is how much energy you can actually get per unit mass. You may have heard that gravity, despite, in our experience, being a pretty weak force, right? I mean, if gravity wasn't so weak, I'd be in a lot of trouble because I would just be a puddle on the floor because my body wouldn't be held together. Gravity would overwhelm me, so I'm very happy that the gravity is weak and I'm not being tidally disrupted by the gravity of the Earth. It's a good thing. But given that gravity is such a weak force, it's kind of amazing that it can actually produce a lot more energy than, let's say, nuclear fusion, much less chemical reactions. So let's just see that very quickly. I have a black hole. My black hole is of mass m, big M. I have a little particle. It's little, so it has mass little m. It's orbiting around the black hole. It's orbiting in an orbit of radius r. The energy of the orbit, well, the gravitational potential energy would be minus g big M little m over r. Now, that's the gravitational potential energy. There's actually, of course, a kinetic energy. By the virial theorem, the kinetic energy is half the magnitude of the potential energy. So kinetic energy is plus gmm over 2r. And when we add those together, I get a factor of 2 over here. Okay, we don't really care about factors of 2, so I'll ignore it from now on, but there should be a factor of 2 there. Now, let's suppose this particle is gradually spiraling in. Why is it spiraling in? Okay, let's not worry about what's causing it to spiral in. Maybe it's gravitational wave emission, maybe it's a viscous accretion disk that it's sitting in, and there's some energy dissipation happening. Maybe the energy is coming out in winds, maybe it's coming out in photons. We're agnostic about this. We're just looking at the total energy output that might be happening here. How far can this particle spiral in? Well, there's a minimum radius for a orbit in general relativity, and that radius is the ISCO radius, innermost stable circular orbit, and it's, for a Schwarzschild black hole, it's 6 gm over c squared. Now, you might say, okay, well, yeah, I need to know general relativity to do this, and you promised me first-year mechanics. This is too hard. Okay, let's do it first-year mechanics. Imagine that where would you put, if you only knew first-year mechanics, the event horizon of a black hole? Well, you'd say, look, it's a surface where from which light cannot escape, right? So light cannot escape means the escape velocity has to equal the speed of light. Well, the escape velocity at some radius r, v escape, is root gm over r. If I set that equal to the speed of light, then, and do a tiny bit of algebra, I see it's gm over c squared equals r. So that tells me the event horizon from classical mechanics should be a gm over c squared. General relativity tells you, you're way off. It's 2 gm over c squared for a Schwarzschild black hole. Factors of 2 we don't care about, so it's good enough. Okay, that's the event horizon. Turns out the innermost stable circular orbit is a little bit further out. Again, we don't care that much about factors of order unity, but we'll use this value. Okay, so if I plug this value into here, then the energy at the innermost stable circular orbit, right, so energy at ISCO, okay, I plug 6 gm over c squared in place of r, so 2 times 6 is 12. Okay, 1 over 12 is about 0.1, so I'll just put a 0.1 over here. Gm over gm, okay, those cancel, and you just have 0.1 little mc squared. Sometimes people write this as eta, sort of the energy efficiency. The point is that you can convert by swallowing little mass, by accreting little mass, etc. You can turn this mass into 10% of its mass energy, right? Okay, the other 90% just ends up falling inside the black hole, and you never see it again. The mass of the black hole grows, and that's it. But 10% actually has to come out if you're going through on this gradual in spiral. Okay, it's not quite the same if you go in on a radial trajectory, because the radial trajectory is a little bit more like a good Olympic level diver, right? So the diver, she jumps off of this 10-meter tower, right, and then she goes in and there's not even a splash, right, because she's such an amazing diver. Okay, of course, she has converted her potential energy into kinetic energy, but then all of that energy goes into the water. Okay, ultimately it somehow heats up the swimming pool, because hopefully our diver emerges safe and sound without too much injury to herself. But in this case, it would be for a radial infall, the energy just ends up inside the black hole, fine. But if it's anything else, if it's this gradual in spiral, you have to get out something like 10% of mc squared, right? If I compare this with the mass deficit of hydrogen, for example, I see that this is already 2 orders of magnitude more efficient than what I can get out of nuclear fusion, for instance, right? So it's actually quite incredible. Of course, that also means that if I think that this energy is coming out in some kind of photons, I get a luminosity that's of order 0.1, okay, m dot c squared, where m dot is the mass accretion rate into the black hole, right? So luminosity is just energy per unit time. So if I divide this by time, I'm dividing mass by time, so I get a m dot. By the way, one exception to this is, well, it's not quite an exception, but one interesting consideration is what actually happens in gravitational waves. So what happens in gravitational waves, at least when you get really close, is that there's a very specific time scale involved, because by the time you're getting close to the innermost stable circular orbit, if you have 2 comparable mass objects merging, the time scale is actually the dynamical time scale of the problem, right? Dynamical meaning something like the orbital time scale. So the dynamical time scale, let's say that my for practical purposes, my two masses are the same, so little mass is the same as big mass in this case, right? So my dynamical time scale, okay, think of Kepler's law, it's going to be something like r to the 3/2 over root gm. And so if I now say, okay, what's my gravitational wave luminosity near the innermost stable circular orbit? Well, okay, it's still this amount of energy that I'm releasing, right? But I'm releasing that energy over this time scale. And so if I plug this in, I actually find that I get something like c to the 5th over g. This answer is interestingly independent. Sorry, is it g times? No, g times c to the 5th. Ah, my units are off. Sorry, wrong units for luminosity. I'm very used to working in units where g equals c equals 1, and so I have to always remind myself when to plug in my g's and c's. Okay. In any case, this is basically like you can think of it as a kind of Planck luminosity, right? It's actually independent of the masses involved. It's independent of the masses involved because the energy scale goes as m, but so does the time scale, right? They both scale with the mass, because if I plug in for here, maybe I should have, okay, sorry. I think I skipped too many steps. So if I put in a typical radius here, right, the radius is, as we learned from here, is gm over c squared. So I have over here gm over c squared quantity to the 3/2 divided by root gm. So that gives me gm and then c over c cubed. Okay, and then the total amount of energy I'm getting is some fraction of mc squared divided by this time scale. So mc squared divided by gm over c cubed. No, I was right. It is over g. Sorry, I psyched myself out. So this is, I do get c to the 5th over g. I apologize. Okay. The energy scale is actually independent of the kinds of masses that are emerging. We're always getting out a few percent of the mass energy of the system on its dynamical time scale when we're getting close to merger. What else can we do that's interesting with this? Well, we can do a few things. Like one thing, for example, is to realize why. I'm just going to use a few random examples of why these calculations are useful, done in this very silly way. So one example is that if you think about this luminosity, and you think, for example, of a neutron star that's accreting from its companion, and you think of the kinds of luminosities you might get out, or the kinds of energy scales you might get out, and you compare that with the binding energy of the companion. If the companion is a very low mass star, you quickly realize that the low mass, you're putting out more energy than the binding energy of the low mass star, even directed onto low mass companion. So that means if you're dumping more energy into a star than its own binding energy, you pretty quickly puff it up and ablate it, and don't have much of a star left. And that's exactly what we think happens with redback and black widow pulsars, right? So if you believe at least that the way that you get black widow pulsars, so pulsars with that have clearly been accreting from a companion but have almost no companion left, well, maybe they come from redback pulsars, which are pulsars which still have a companion but a very low mass one, maybe 0.1, 0.2 solar masses. Then it seems that the reason that you're actually ending up with such a low mass companion is just because of the luminosity you're putting out through accretion. It's so large that you're ablating away the companion. And you can do this calculation very straightforwardly and convince yourself that yes, indeed, you have more than enough energy to ablate away the companion. Another way to make use of this is to compute the Eddington luminosity. So people have probably done this many times, but just as a quick reminder, consider some gas of density rho, again at the usual radius r. I have some big mass m sitting in the center. This gas has a mass dm, which is r squared rho dr. Dr is the thickness of the shell. Yes, there's a factor of 4 pi. I'm lazy. Let's say that this gas has some optical depth tau. So the optical depth tau, generally speaking, I just mean in this case, well, it should be an integral of kappa, the opacity, times rho times dr. But if dr is small enough, it's just kappa rho dr. So that means if I want to know if I pick a thin enough shell that most of my photons just stream through, only a small fraction of the photons actually interact with and are scattered off of the gas in the shell, then I quickly convince myself that only a fraction of the outward momentum of the photons is going to interact with this gas and push out in it. That fraction is given by tau. So the outward momentum of the photons is L over C, because the momentum energy relation for photons is energy is P, the momentum times C. So if I want to go from energy over time to momentum over time, I divide by C. So L over C times tau has to, this is how hard I'm pushing on this gas outward. That has to, at some point, if I push out on this gas too hard, then it matches how the force of gravity that's pulling on the gas inward. Of course, the force of gravity pulling on the gas inward is gm dm over r squared. And I look at this and I immediately realize that sets a maximum luminosity. And if I make some assumption about how luminosity is connected to the mass accretion rate, then it sets a maximum accretion rate that my gas can maintain before it's blown away, right? So this is the famed Eddington luminosity. So if I plug in for tau, I plug in rho kappa dr. For dm, I plug in rho r squared dr. R squareds cancel. That's good, because this means that my answer will not depend on where I drew this imaginary shell. Rho dr cancel, and I have the Eddington luminosity is proportional to g m c over kappa. And then I can plug in a mass accretion rate here, because I say the Eddington luminosity is something like eta times m dot c squared. So that gives me a m dot Eddington, which looks like gm. Okay, I now divide by c, and I divide by eta, and I divide by kappa. That's not a very useful way of writing it, so maybe a more useful way of writing it is actually noticing that this is proportional to the mass. So the Eddington mass accretion rate is about the mass divided by something like 30 million years. Why is this useful? Well, it's useful for lots of different reasons. By the way, I should say 30 million years depends on the actual opacity kappa, so depends a little bit on the environment that you're in, because the environment you're in sets the opacity, whether, for example, it's dominated by the scatterings between photons and electrons, in which case it's Thomson scattering opacity, order of magnitude point few centimeter squared per gram for ionized hydrogen plasma. But of course, there will be other environments where other opacity sources dominate. Two examples where this is relevant. One is spin in high mass X-ray binaries. So high mass X-ray binaries consist of a black hole and a companion star. The companion star is losing winds. The winds are, some of the winds at least end up in an accretion disk and accreting onto the massive black hole. Cygnus X1 is a famous example of this. In our own galaxy, consists of a 20 solar mass black hole and a 40 solar mass companion. Other examples include LMC X1, M33 X7. They all seem to have fairly large black hole spins. Now, why is that a puzzle? Well, it's a puzzle because the lifetimes of these high mass X-ray binaries are much less than 30 million years. The stars that make them just don't live for that long. Massive stars have lifetimes of only a few million years, and the difference between the age of the black hole and the age of the companion is even less than that, perhaps tens to hundreds of thousands of years. So you don't have enough time to accrete enough gas, right? This basically tells you the mass doubling time through accretion is tens of millions of years. that means you cannot accrete more than a few % of the mass of the black hole. And it turns out, and again, this is a back-of-the-envelope calculation, we just might not have time for it, but it turns out that whereas for a star, if you accrete a few % of the mass of the star, you actually can spin it up to near breakup. A black hole is so compact that it's such a small lever arm that you really can't do much unless you double the mass of the black hole. It takes doubling the mass of the black hole in order to appreciably change its spin, to change its spin from 0 to 1. You can actually, it's a very simple calculation. You can just imagine that, the usual specific angular momentum that you write as r cross v. Okay, plug in here the radius of the black hole, which is order of magnitude gm over c squared. For velocity, plug in the speed of light. Okay, at the innermost stable circular orbit, you're actually moving at something like 40% of the speed of light, but let's plug in the speed of light. So you find specific angular momentum is gm over c. So if you want to know, okay, the total angular momentum of black holes, when people talk about dimensionless angular momentum, chi, they really mean total angular momentum in units of mass squared, with some g's and c's in there that I have to remind myself where they go, so I'll, for a moment, just ignore g's and c's. So I'll also ignore g and c over here, and I will then say, okay, if I want chi to get to 1, how much mass do I need to accrete? Well, it's very simple. The total amount of angular momentum, specific angular momentum, times the amount of mass accreted in units of mass squared. Okay, this is m, specific angular momentum. So it's m delta m over mass squared, which is just delta m over m. And if I want this to be of order unity, because I want to spin up my massive black hole, or my stellar mass black hole, from non-spinning to rapidly spinning, dimensional spin parameter of 1 is the largest spin that a curved black hole can have. I need delta m to be of order m, right? So that's my one-line proof for why I would have to roughly double the mass of the black hole in order to bring it from non-spinning to maximally spinning. And I don't have enough time to do that in a high-mass X-ray binary. So the observational claims that black holes in high-mass X-ray binaries are rapidly spinning are genuinely a big challenge, because it's not obvious how to spin up those black holes. Now, you might say they're born rapidly spinning, but it's also not obvious how to form rapidly spinning black holes in tight systems, because the general picture is that, yes, progenitor stars can be rapidly spinning, but remember, in a tight binary, generally speaking, as the star expands post-main sequence, most of the angular momentum goes into the envelope, because the moment of inertia is all out here in the envelope. And when binary interaction strips off the envelope, you remove most of the angular momentum, so you're left actually with a slowly spinning remnant. So it's actually not that easy to, in this very naive picture, to form a rapidly spinning black hole in a tight binary, such as a high-mass X-ray binary. Another example, by the way, where this comes in is, I mentioned earlier that the most massive stars sort of asymptote to a fixed lifetime of a couple of million years. It actually comes from the same calculation. Because if I look at this, I say, okay, well, this tells me what the maximum luminosity is a star can produce, and it's proportional to the mass. How much energy does a star need to radiate away? Well, it has to burn a significant fraction of its hydrogen into helium. I know what is the total mass deficit of hydrogen, so I know what fraction, how much energy per unit mass the star produces. It's just a fixed amount, right? 0.1% or something like that, 0.2%. Now, the point is the energy that a star has to produce in total over its lifetime, by the time it's done fusing hydrogen to helium, is linearly proportional to the available mass. So energy is proportional to mass. A star cannot output too much luminosity because it'll blow itself up. So there's a maximum limit to the luminosity that a star can produce, which is proportional to the mass. And so the time scale, the largest time scale, shortest time scale, sorry, over which the star can produce that energy, well, actually it's not dependent on mass, because time scale looks like energy over the rate at which you can generate energy, but we just said the rate at which you can generate energy is limited by the Eddington limit, so it's energy which is some fraction of mc squared, given by the hydrogen mass deficit. You were dividing it by energy derivative, which is, in this case, the Eddington luminosity, which is, again, something that's, some other constant that's proportional to m, and the masses cancel, and so this just becomes a constant. And so it actually turns out this constant is about 2 million years. So that's the shortest lifetime of massive stars to reach the asymptote. Now, I mentioned high mass X-ray binaries, and I said, look, in high mass X-ray binaries, you are accreting mass from winds. Okay, that's a simple enough story. But remember, earlier I also said that you need to, in order to produce energy, you kind of have to have the mass spiraling in. You kind of just have it falling in radially. And this turns out to be actually very important for understanding a very weird thing about black hole high mass X-ray binaries. They're all incredibly tight systems. They're still wind-fed, which means that the donor star is not overflowing its Roche lobe, which is just a fancy way of saying the donor star is not yet being tidally disrupted by the companion, so it's within its own effective potential boundary. Its self-gravity wins out over the gravity of the companion. Okay, that's all good. So it has to be accreting from winds. Okay, these massive stars have strong line-driven winds, plenty of masses coming out. You can do a simple calculation and convince yourself that a non-negligible fraction will end up in the companion black hole just from Bondi-Hoyle accretion. You do this calculation, you convince yourself that, yeah, okay, closer binaries, you do have some preference towards them, tighter binaries, because if the companion is closer, then a bigger fraction of the outflowing gas ends up in the companion. The companion sort of presents a bigger target, relatively speaking, on the sky. That's all good. But then you think about it and you say, well, but okay, at least some of these should have the donor that's maybe only filling half of its Roche lobe or 30% of its Roche lobe. All of them are like 90% plus Roche lobe filling. What's going on? So this was a big puzzle, and a couple of years ago, my postdoc, Ryosuke Hirai, figured out the answer from first principles. So I'll take the remaining 2 minutes to tell you about this. And this is actually a place, it's also a warning, because it's a place where back of the envelope calculations sometimes give you the wrong answer. So we were having this conversation with Rio, and we were talking about the fact that, well, you need to have enough angular momentum in the gas to form a disk. Because, as I was just saying, if you don't have enough angular momentum in the gas, meaning that the specific angular momentum of the gas is less than the specific angular momentum at the inner edge of the presumed disk, at the innermost stable circular orbit, then you just have spherical accretion, and that's like the amazing Olympic dancer just diving into the pool and not creating a splash. Nothing is coming out, the black hole grows in mass, but we never see it as a X-ray binary. So I said, but Rio, come on. There's plenty of angular momentum present. And we did this calculation, and I won't waste your time because you have to be a little bit careful about how you compute angular momentum in this case. But we did the calculation, and there was almost a factor of 1,000 in favor of having, the amount of specific angular momentum was like a factor of 1,000 larger than that of the innermost stable circular orbit of the disk for typical parameters. So we're done. Clearly, there is always enough angular momentum. It's not an issue. Well, fortunately for me, Rio is much more careful than I am, and he went back and did the calculation carefully. Turns out this is one place where you have lots of factors of 2 and pi, and they all go in the same direction. They give you about a factor of 2,000, going the other way. So actually, you conclude the exact opposite. You conclude there is no such thing as a wind-fed X-ray binary with a black hole, because you never have enough angular momentum to form a disk. Okay, except we see Cygnus X1, and it produces X-rays. Well, did I say that Rio is very clever and very careful? So he figured out something else that happens. The calculation we did initially assumed you have a nice spherical star with a nice spherical wind that's accelerated in the usual way that you expect by, given the luminosity of the star, all is nice and straightforward, except, of course, that when the binary gets very close, the companion star is tidally distorted. A star doesn't look spherical. If I put a star close enough to a black hole, here's my black hole, my star looks something like this. And when badly drawn, my star looks something like this. Anyway, it is a misshapen star, although I'm absolutely terrible at art. And this misshapen star, it's very severely gravity darkened on this side, so its luminosity is very non-constant over the surface. Because we're talking about line-driven winds, it doesn't just, the gravity darkening, first of all, impacts the mass loss rate, so mass loss rate is not uniform over the star, but also the acceleration is impacted because for line-driven winds, it's the photons coming out that are pushing out on the gas and accelerating it, so it's changing the ultimate velocity of the gas. And so overall, the morphology of the gas flow is changed very significantly if your star is sufficiently distorted. And it turns out it's only important the star is sufficiently distorted, but from first principle calculations, Ria was able to show that if the star is more than 80 or 90% Roche lobe filling, the boundary is somewhere between 80 and 90%, depends a little bit on the assumptions you make about wind acceleration mechanisms. But naturally, that's the dividing line where you go very rapidly from having almost no angular momentum to having lots of angular momentum in your flow, meaning you can form a disk, meaning you can form a radiatively efficient high mass X-ray binary. So there's your answer. I didn't get to talk about common envelopes, but if people have questions, I will be happy to talk about them or anything else. Thank you for listening.
Okay. Thanks a lot for all of that. I guess it's pretty informative for a lot of people in here. So yeah, questions?
Hi, Ilya. Hi, Ilya. Great talk. The 80 to 90% Roche lobe filling result, does that have, it sounds like it would have extreme implications for, say, the observability or the lifetime of these. If you're so close to Roche lobe filling, it wouldn't take much to fill the Roche lobe and then probably merge the system, I guess, or something. Is that the case, or am I missing something here?
No, you're absolutely right. It is the case. We think that this, in fact, explains the rarity of these systems, right? I mean, we know of only one black hole high mass X-ray binary in our galaxy. Cygnus X1 is the only one we know. You're absolutely right that we think that, first of all, it takes a very special kind of system to ever get there, because if you start out, for example, with a binary that's too wide, it won't ever reach the stage of being 80% Roche lobe filling while the optical companion is on the main sequence. But even among those things, it can be very short-lived. We're talking about tens of thousands of years, typically, for typical lifetimes. There might be some caveats to that. Some systems, we were actually just discussing this with Pablo yesterday, might go in a regime where the companion does overflow the Roche lobe and then sticks around in a closed binary, sort of detaches at some point, and is again wind-fed. So you might have some intermittent stages of Roche lobe overflow, wind-fed system, Roche lobe overflow, wind-fed system. So that might prolong the X-ray binary, wind-fed X-ray binary lifetime in total, but we're still talking about 100,000 years, sort of ballpark tops for these kinds of systems.
Okay, thanks. If I can maybe permit just one more. If I have a particle on the inside of our ISCO, what happens to it that causes that to be unstable? Is there an intuitive way that I can think about this? Or?
So you're absolutely, so it is unstable. So what it means is that basically this particle will, in practice, generally speaking, very quickly plunge into the black hole. So it plunges in, so you're sort of gradually spiraling in. And then once you go inside the innermost stable circular orbit, you plunge in on a dynamical timescale. So over the course of less than one orbit, you go from being at 6 g/c squared to plunging in. The best way to think about that is to draw the effective potential. The ISCO is a kind of minimum of the effective potential, but it's, or maximum actually the effective potential, but it's actually not this part is hard to do without doing some general relativity, but the effective potential looks something like this. So this is radius, this is V effective, and so you can imagine, okay, over here, particles happily sit around, you have the usual potential well, particles can move around and be there quite safely, right? And then there is this is your R ISCO, and if you go anywhere inside of that, you end up just very rapidly falling into the black hole. Now, this will not happen in classical mechanics, right? This is a GR effect. In classical mechanics, the potential just goes like this, right? So that part, yeah, we'd have to actually write down the Schwarzschild metric, so it's going to take more than 2 minutes.
Yeah, no worries. Thanks.
Okay, other questions? Yes. Over there first.
So first of all, thank you for the amazing Blackboard talk. I really like it when we can get follow along. Of course, C and G are equal to 1. I have to agree completely. But my question is rather on the first picture you showed, right? You're saying now we have quite a lot of mysteries when we detect gravitational waves to understand, how are these systems even produced, and we are using quite a lot of population synthesis models to try to infer what future detectors, so I'm talking Einstein telescope, Cosmic Explorer, and LISA will see, right? This is very important for us to know whether these specifications and the noise measurements of these systems are well defined. Do you think at some point we will get to a point where these measurements are numerous enough and statistically significant enough that they actually can inform the other way around and tell us about what our population models are either right or wrong? Or is that not possible with what gravitational waves tell us?
I think that's absolutely possible. I think, in fact, that's sort of one of my research goals. I call it gravitational wave paleontology. So the idea is that in the same way that a paleontologist who has presumably never seen a living, walking dinosaur can look at the bones, the fossil record, and figure out from the bones, using her knowledge of anatomy and physiology, whether this dinosaur was a carnivore or herbivore, and if it was a carnivore, whether it lived alone or it hunted in groups, and so on, all from just the fossils, right? We can play similar games. You can think of black holes and neutron stars as fossils of massive stars, right? The massive star dies in 2 million years, as we just said. It leaves behind a black hole. That black hole can then survive for 12 billion years before it merges with something else, right? So some of these things that we're seeing today merging in the local universe may have formed very soon after the Big Bang in the very early universe, right? Redshift 20 or something, and are or redshift 10, and are only merging now after a long delay time in the local universe. And so this is, in principle, giving us a handle on binary evolution, but also even on some aspects of cosmology. For example, we can think about probing the metallicity-specific star formation history of the universe, for example. Of course, the challenge is we also have lots of uncertainties in our models, as you rightly said, and so I don't think gravitational waves alone are going to be enough, because, okay, you get to measure only a few parameters at the moment of merger. You get to learn something about the masses and the spins of these objects, and maybe the spin-orbit misalignment, but you don't really have maybe eccentricity if you have eccentricity in these systems, but there's a limited amount of information you can glean from two merging black holes, right? Black holes are kind of these very simple objects, so they're beautiful, but they're also, simple means they're only described by a couple of numbers, right? An astrophysical black hole just has a mass and a spin, and that's it, right? So there's only so much you can learn. And so I think we do need to pull in other information, other observations, gamma ray bursts, galactic double neutron stars observed in the radio, supernova observations, observations of X-ray binaries, observations of luminous red nova if you think these are accompanying common envelope events, and so on, right? And I think it's only by building some sort of a concordance model that can be tested against all of that observational data can you actually do the inference and learn astrophysics and cosmology from gravitational wave observations.
Thank you.
Hi, Ilya. I was intrigued by the last. I was actually not aware of this result by Ria. It's very nice. One aspect, it might just be a detail in the scheme of things. I would have to, read up on your results. But as you are very well aware, of course, when you create a distorted star, you don't have any flux basically over the equator. So also your wind outflow becomes mostly over the poles, right? You don't have anything. Did this at all affect your conclusions about the wind-fed X-ray binaries, or did you only look at, so to say, the global picture and you assume that it got captured anyway, so to speak?
Yeah, so we tried to do sort of the model of the wind.
I mean, you can do it analytically as well, actually.
You can, but there are caveats, right? So you're absolutely right that we oversimplify things a fair bit. So one way that we oversimplified them, for example, is that we considered, when we talked about the wind acceleration, we sort of momentarily imagined that the wind was being accelerated, along the line along which the photons were moving, right? And so if you look at a given patch on the surface of the star, and the luminosity of that patch, which is, because of gravity darkening, is dependent on the direction, we just say, okay, great. So all the photons from there are moving straight out, and that determines the acceleration in that direction. But in fact, that's actually, photons get scattered. They don't move straight out, and so there's a more complicated picture. We also didn't, for example, properly account for the hydrodynamics because you have this much more complicated flow, and we sort of said, okay, well, what's the average specific angular momentum? But in fact, you have, in principle, if you do detailed hydrodynamics, you would have to worry about the fact that in some places you have stream-stream collisions, for example, and that will change the morphology further, right? So I think there is still plenty of work to be done. So yes, I think this result in some ways is somewhat preliminary. One interesting side note, by the way, for example, is that because the winds end up being much slower than you typically think because of gravity darkening and the reduced wind acceleration, it means that winds can actually be slow relative to the orbital velocity. Now, what that does is that it means that in the typical picture, we always say, okay, if we have infinitely fast winds, the binary widens, right? If I just remove mass magically from a star in a binary, and I think about what happens to the angular momentum, the binary has to widen, right? But here, that's not the picture, because in this picture, actually, you have winds that experience drag and that form a wake behind the companion. And so they're dragging back on the companion. So in fact, you might actually have binaries that are either widening less or even being hardened by the wind. Now that, for example, is an extra complication in terms of Alex's question about the lifetime of these things. If they're being brought closer in very efficiently by winds, then you might worry that these things are going to be very short-lived indeed in this phase. So these are all, you're totally right that there are lots of other things one has to do carefully. It's on the to-do list, but there are lots of things on the to-do list, so we'll see whether we ever get to it.
That's nice.
Thanks, Ilya. The obvious question, right? So Simon wants to backtrack you from gravitational waves. I want to forward model you from astroseismology that has measurements of how internal mixing does happen in reality, and also the shapes of the stars in their interior. I don't think your community is using these constraints so far, so I would like to see that change.
I think I could not agree more with your point. I think you're absolutely right. Of course, one of the challenges is that I was talking here mostly about very massive stars, right? And of course, there are, as you know better than everybody, there are special challenges in those observations. But indeed, one of the things, for example, that's very interesting is how efficient is angular momentum transport in stars. And we have, I am interested in astroseismology. I know very little about it, but for example, I've been working with my colleague at Monash, Andy Casey, and his student Tanner Wilson, and we were sort of trying to see whether observations of subgiants can help us figure out something about the where the boundary is between the core rotation rate and the envelope rotation rate, and use that to constrain something about angular momentum transport mechanisms within stars. So absolutely, I 100% agree that this is a very important set of data that should help us understand and improve these models.
I know that we have to go to higher masses. We're working on it by the day. I agree with that.
Thank you.
Okay, so let's thank Ilya once again.